For our next section, section 11.2 on series, we are going to take a look at our sequences and turn them into infinite sums. So just to start off, our definition of a series. A series is an infinite sum of a list of numbers, and another way to think of that is the infinite sum of a sequence. So we're going to take all those sequences, all that theory about sequences from the first section in this chapter, and now we're going to take a look at it, and rather than looking at it as a list, we're going to look at it as a sum. So we're going to add in sigma, the summation notation, and add up all of the terms in the sequence. And we're going to talk about this infinite series and consider what happens to this infinite series. So why would we want to do this? Well, we have a lot of theory to build up. But if we go all the way back to when we talked about integrals and how we can't actually integrate every function, this is going to ultimately allow us to, if we can come over here to the side for a second and think about for a second just this integral that we were unable to integrate with our integration techniques. So how do we integrate this? Well, we talked about numeric strategies. This came up at the end of chapter 7. So how do we integrate? And we don't have the ability to do that right now. So what do? Well, ultimately, what we're building up some theory here to do is to say, if I could come in here and I could look at this function, if I could think of this function, f of x equals e to the x squared. And if there was a way that I could actually write that as what's thought of as an infinite polynomial, if I could write that as an infinite polynomial, well, I know how to integrate an infinite polynomial. That we can actually integrate. So if I could, we can integrate this. So if I could write that function, e to the x squared, as an infinite polynomial, well, we can integrate polynomials, and I'd be able to find this integral. So that's just a little preview of where we're headed. It's going to take us a while to get there, and I'll try to remind us of where we're going. But this is ultimately the theory that we're building up, because we're a little limited in what we can, not a little bit, we're quite a bit limited in what we can integrate. But if we can represent functions as polynomials, infinite or otherwise, then we can actually apply some integration strategies to them. Okay, so there's our little preview, there's our little reasoning. So that's why we're going to build up this theory around these infinite series and determine where these series have sums. Okay. So, but before we get into any of that, before we introduce the variables and all of that, let's talk about just the general idea of a series. So here's an example. If you had a sequence, a sub n equals n over n plus 1, then we can turn that into a series by looking at what is the actual infinite sum of those terms. So we'd be looking at the sum 1/2 plus 2/3 plus 3/4 plus 4/5, and this goes on and on. This is an infinite sum. So that's just our first example of a series. So what are some basic rules for manipulating series? Because we will want to manipulate some series. So we can pull a constant. So these are just some summation rules. We can pull a constant out. Notice that there's no index on this first rule because the index is irrelevant. If we're adding two series and they start at the same index, then we can add or subtract, actually. We can add or subtract the individual series. And if we wanted to split up a series, if we wanted to break apart the sum, we can do that. And we can look at it as the finite sum plus an infinite sum. All right. Another thing we can do is we can do some re-indexing. Sometimes that helps us when we're looking at these series. For whatever reason, we might prefer the index to start at a different number. So notice on this particular one, this example I have here, n is starting, the index is starting at 2, and this is the series n plus 5 over 2 to the n. So the denominator is increasing powers on 2, and the numerator starts based on the index start of 2. The index starts at 7 and increases each time. So 7, 8, 9, 10. So if for whatever reason I just wanted to switch that index, I wanted that index to start at 0, say, I can do that. I just have to do a variable change here. And so I could say, well, if I want the index to start at 0, I need to subtract 2 off of that initial start. So I would say let I equal n minus 2, and then I just make those adjustments. So then n is I plus 2, and I replace that throughout the series. So notice what we're doing here. And this is switching the index. So now I've got the series I plus 7 over 2 to the I plus 2, and it generates the exact same series. So this is just a little example of re-indexing. Sometimes we do this as we're working with a series if we don't like where the index starts for whatever reason. Okay, well, why would we do this? Like, why do we want to add up an infinite list of numbers? Well, I mentioned earlier that the reason is because we're building up to a place where we're going to be able to use this theory that we're working on here in order to get back into some integration and look at integrals that we have been otherwise unable to integrate except with numeric estimation techniques. So when we have a series, we have to think about it in two ways. One, we think about the fact that it has a list of terms, the a sub i's. And we also think about the fact that it creates a second sequence of terms that is what are called the partial sums. So the partial sums are looking at each of the sums as we increase the index. So S1 would be the sum of the first term, and S2 would be the sum of the first two terms, and S3 would be the sum of the first three terms, and S4 the sum of the first four terms, and Sn is the sum of the first n terms. So this is the sum of the first n terms. Anytime we say S sub n represents the sum of the first n terms. So the sum of the first n terms. So keep in mind that each series that we look at actually has two sequences that we're going to consider. It has the sequence of the actual terms themselves, and then it has the sequence of the partial sums. So we'll reference back to that a lot because when we talk about these series, we're going to look at both the sequence of the terms, but we're also going to be considering what's happening to the sequence of these partial sums. Okay, so let's take a look at what it means to converge as a series. So as a series, we say that we converge if the partial sums, if the sequence of the partial sums is convergent. And if it converges, then we say that it converges to some limit. This is important here, I'm going to highlight it. Some limit S if our partial sums have a limit. So if we're looking at those partial sums and they happen to approach, they have a finite limit, then we say that the actual series is convergent. If, on the other hand, the partial sums, for whatever reason, it could be that, remember that sequences can diverge for a variety of reasons. They can diverge to infinity or negative infinity. A sequence can diverge through oscillation. So there's multiple reasons why a sequence itself is divergent. But if the sequence of partial sums is not convergent, so if the sequence of partial sums is not convergent, then we say that the series is divergent. Okay. So a lot of language, a lot of definitions, and we're going to get into what does this mean and how do we show convergence or divergence. So let's just start off with this harmonic, what's called the harmonic series, 1 over k. And I'm going to use k for this first one rather than the index of n because I want to use n when I talk about the partial sums. So let's go ahead and I'm going to come over here so I have a little bit more space and let's take a look at this harmonic series. So the harmonic series, that stems back from its connections to music, actually. We'll take a look at this guy a few times, but the harmonic series 1 over k from k equals 1 to infinity. And so let's just take a look. If I were to write this out, this would be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. We'll go a little bit further. On and on. This never ends. So the actual, notice here, we end up with two associated sequences. So the sequence of terms, just the sequence, and I'll call them a sub k's. The sequence of terms, themselves is the list of terms we have here. 1, 1/2, 1/3, 1/4, 1/5, and so forth. Now, the sequence of partial sums, on the other hand, is going to take a little bit more time. I will list it down here, but let's take a look over here first. So if I want to come up with the sequence of the actual partial sums, I have to think about, well, what would the partial sums be? So the partial sums if I wanted to come up with what the partial sums are, I have to think about, well, what's S1? What's S2? What's S3? What's S4? What's S5? And we're going to keep going. So S1 would just be the sum of the first term, 1. S2 is going to be the sum of the first two terms, so 1 plus 1 half. And 1 plus 1 half, of course, is 3 halves. And then I would have the sum of for S3, for the third partial sum, I'm going to add up the first 3 terms. So that would end up being, when I add that up, that becomes 11/6. And then the first 4, 1 plus 1 half plus 1/3 plus 1/4, and that ends up giving me 25/12. And then the fifth partial sum. And we can keep going. 1 plus 1 half plus 1/3 plus 1/4 plus 1/5. And that ends up giving me 137/60. Okay? And this keeps going. And I'm going to come back to that in just a second. We'll look a little more at those partial sums. But that gives me, that list of numbers right there, gives me my second sequence that is associated with this series. So now we have the sequence of partial sums. And the sequence of partial sums, S sub n, would be the numbers 1, 3 halves, let's see if I can remember to get those on the screen, 11/6, 25/12, 137/60, and on it would go. Okay. So for a series itself to converge, this is the sequence that we're looking at. So we're looking to determine if the original series, to determine if the series, if a series converges, we look at what happens to these partial, we consider what happens to the limit of these partial sums. So do these partial sums, as we continue to add more and more terms into these partial sums, does that new list of numbers have a limit? Does it approach a finite value? Now, that is not necessarily an easy task. Okay, so it seems like, well, we did limits of sequences in the first section here, and it wasn't too difficult. We applied all of our limit rules, but this is actually not necessarily the easiest task to figure out if a series converges. So we're going to go through a few things. I want to show you why it's not necessarily the easiest task right here. The reason it's not the easiest task is because this piece right here is not the easiest to find an explicit formula. So it's not the easiest task because this can be difficult to find. It's difficult to find an explicit formula for this. An explicit formula for S sub n. So it's a little bit difficult to find, or not a little bit, it can be difficult to find a explicit formula for S sub n, and finding that explicit formula for a sequence is what allows us to be able to take that limit. So since that's difficult to do, we have to come up with some other strategies. So there are some series, don't get me wrong, there are some series that we can write an explicit formula and apply our limit rules to. So we'll explore those first. But for the ones that we cannot do that for, we have to come up with another way to determine convergence. And that's going to lead us into all of our what are called tests for convergence. And so the next several sections we'll talk about tests for convergence. But before we get there, let's just take a look. Like if for this particular one, there are actually several ways to show what happens to this. And I want to just go through one quick one since we started writing out the partial sums over here. I want to go through just one quick little way to talk about what happens to this harmonic series to show that this actually diverges. This is not going to converge to a finite number. So if I just come back over here and I take a look at, here are my partial sums, and let's start by looking at focusing in on each of the powers of 2, looking at the index when it hits a power of 2. So for instance, let's look at this guy, and then let's go to S4. And on S4, what I want to do here is I want to focus on these two terms. And so we know that this equals 25/12, but if I come and I actually think about those two terms, those two terms, if I were to say, let's replace the 1/3 with a fourth, and if I replace the 1/3 with a fourth, then I could say that this has to be greater than, let's see if I can get this all on the same screen. This has to be greater than 1 plus 1/2 plus, and I'm taking that 1/3 and I'm replacing it with a fourth plus, and then we already had the fourth. And notice I had to switch this to, rather than equality, I had to switch it to an inequality and say that that is now greater than. Well, if that's, so there we can go. We can say that that's greater than that. And then we can jump down here, and I want to jump all the way down rather than looking at S5. Let's keep going and go all the way down to dot, dot, dot. Let's go to the 8th partial sum and look at that. So this would be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. And I can say this, I'm going to group these as well. So I'm going to group these 2 and I'm going to group these 4. And I can say now that this whole thing has to be greater than 1 plus 1/2 plus, and then we've got that 1/4 plus 1/4, which we know that turns into 1/2. I should have written that up here too. This is 1/2. And then we can add, that's also going to end up being, if we replace the 1/5, the 1/6, the 1/7, and the 1/8 with 1/8, 1/8, 1/8, 1/8, which we can do because we changed it to an inequality. Remember, we've changed this into a greater than here. Well, then this whole thing right here is also 1/2. So notice here I end up with 2 1/2s. So this is actually equal to 1 plus 1/2 times 2. And this right here ends up being equal to 1 plus 1/2 plus 1/2, 3 1/2s, and I get 1 plus 1/2 times 3. So taking a look at that number right there, I know it's going to be hard to get all on the same screen, so I'm going to have to shrink it down. So taking a look there, notice that if we rewrite these, if we write this as S to the 2 to the first, we could write this as S 1 to the 0 power. I'm sorry, 2 to the 0 power. 2 to the 0 power. So small. 2 to the 0 power. And I write S4 as the partial sum of 2 squared, and this would be the partial sum of 2 cubed. We can actually say this. If we look at these partial sums and we focus in on just those partial sums where we end up with 2 to the nth. So the partial sum at 2 to the nth, this would actually be equal to, or actually greater than, that has to not only be equal to, it actually has to be greater than 1 plus 1/2 times n. And notice what's going to happen to this 1 plus 1/2 times n. If we take the limit of this, if we take the limit as n approaches infinity of 1 plus 1/2 times n, this is going to be infinite. This approaches infinity. And we are saying that our partial sums are greater than infinity. So therefore S of 2n is greater than infinity as n approaches infinity. That's what this line right here is saying, that if we know that our partial sums are always bigger than 1 plus 1/2 times n, then as we approach infinity, the partial sums have to be bigger than infinity, which means that therefore the limit as n approaches infinity of S of n has to be equal to infinity, and the series diverges. If the partial sums do not converge, then the series itself is diverging. So that was a long way to show, but I wanted to illustrate that it's not that easy to show that these series necessarily converge or diverge, because in order to, at this point, the only way we have to do that is to show that the sequence of the partial sums is converging or diverging. And if finding a way to explicitly express the partial sums is difficult, well, then it becomes a difficult task to show if it's converging or diverging. So we're going to get into all kinds of theories, strategies, build up a bunch of techniques, and add to our toolbox of ways to show what's happening to these partial sums. But that's our first illustration of a series. So one thing to take away from here, and I want you guys to remember this, that there are two associated sequences with every series. There's the sequence of the terms, right? The terms themselves, just the list of the numbers we're adding up. And then there's the sequence of the partial sums, and it is the partial sums. So there's the sequence of the terms, and there's the sequence of the partial sums. And we're going to be looking at that sequence of partial sums when we consider what's happening to these series, these infinite sums. What's happening to these infinite sums? Do they have a finite value, or is it diverging for whatever reason? That maybe the sum is infinite, or the sum oscillates, whatever it might be. All right, so our next video will do some more examples of some specific types of series that actually we can express their nth partial term and take a look at what happens.